Hello, everybody. Thank you very much for joining us in this webinar series. Today is probably the ninth lecture. Speaker is Peter Cleft. Peter is professor of petroleum geology at Louisiana State University, USA. He'll be talking about the tectonic and climate controls on sediment flux to the Indus submarine fan. We obviously had a few lectures before that, and I had been sharing the links for those lectures. So those people or those participants who just joined us can retrieve those lectures and go through them. We have few speakers lined up. Bob will be discussing their names and their probable dates, tentative. This seminar is a very open-ended seminar. We are still getting a lot of interest from speakers around the world. So if you find yourself interested and you think that your talk can be tuned to the theme of this seminar series, then you can write to Bob or myself or Mukhtar Ghani. We are very thankful to Mukhtar Ghani from Geological Survey of Pakistan, who is sitting in Quetta and is coordinating and web hosting all these programs. We understand it's very tricky and hard job, but we are really thankful to the GSP's support for this. I'll now let Bob introduce the speaker and take on the program further. Bob, over to you.
Yeah, thank you very much, Irfan. And Irfan is from the University of Peshawar, from the Center for Excellence in Geology, and he's currently in Calgary. So we've got, we're coordinating from Calgary, and I'm in Denver, and Mukhtar is in Quetta. So we've got a globe-spanning team here working on this seminar. I will mention that with the next couple of seminars, we've got Andrew Miggs from Oregon is going to give our next week's seminar. He's going to be dealing with structural geology and earthquakes, seismicity. And the next lecture the following week is going to be from Kay Berensmeyer from the Smithsonian in Washington, D.C., and she's an expert on fossil preservation and paleo environments. And then following their presentations, we've got a series of people, including a fellow from Jason Head from Cambridge, who'll talk about reptile fossils. We've got Turi Serling, who'll talk about isotopes. Lisa Taux will talk about paleomagnetics in detail. I've got Yani Najman. She'll talk about the structural geology and controls on sedimentation, perhaps in India. Peter Zeitler is going to give a talk, and he'll talk probably on provenance. And then Javed Khan will probably talk about some of the trans-Indus work that he's worked on in the mountain ranges west of the Indus River, looking at the development of those mountains. But this evening, it's, of course, our great pleasure to have Peter Cleft with us from Louisiana State University. And Peter's a marine geologist, so you might say, well, that's a long way away from the foothills of the Himalayas and the Shawalics, but Peter's been studying the Indus fan, which of course is the material from the Indus River being carried out into the Arabian Sea or the Indian Ocean. And there's a fantastic record of sediment preserved in the Indus cone. And Peter did his PhD at the University of Edinburgh, and you'll hear an accent coming from the British Isles, if I can speak broadly. I think that might be right. And he worked on the geology, the marine geology offshore Greece for his dissertation. And he's been on a wide range of deep sea drilling program expeditions. So he's not only a marine geologist who talks about marine geology, but he's been on the oceanographic expeditions that have gathered the actual data. So, and he's presently teaching at Louisiana State University, which is it's down near New Orleans. It's, I think, in Baton Rouge, and it's a program that has a strong petroleum aspect to it, and a very applied issue of understanding sedimentary geology from the standpoint of hydrocarbon exploration. So I'm going to turn our presentation over to Peter, and we're going to keep the presentation will be about 45 minutes, and then we'll have an opportunity at the end for questions and answers. But Peter, welcome to the seminar, and thank you for being here.
Thank you for inviting me. Let me share my screen here, and we will be able to get this show on the road. So hopefully, well, you probably see the map now.
We do. We see the map. Yes.
Yeah, we do, Peter.
Maybe before I go on with my presentation, I just wanted to show you some of the areas that we'll talk about. I'm going to talk about. So this is the Arabian Sea. And what you can see here in colored dots are the different scientific boreholes that have been drilled over the years, going back to the deep sea drilling project in the late 1960s and 70s, actually into the 60s. The ones in particular I'm going to be talking about today are these here offshore of Western India in the Lakshmi Basin, and a little bit about this borehole, Indus Marine A1, which sits on the Pakistan shelf. I also would like to point out that there's been quite a lot of drilling over here in the Bay of Bengal as well. A big transect was drilled just before our drilling in Lakshmi Basin. There was a series drilled here across the Bengal fan, and then further down here on the tip, the Nicobar fan here, shortly before the sediment is going into the Sunda Trench here. And that's, of course, part of, if you zoom out, you can see that there are a lot of these boreholes. But if we're interested in the sediments related to the generation of the Himalayas and the erosion related to the monsoon, then these are the ones we're particularly interested in. And you'll see there's some interesting records here from the Oman margin that I'm going to touch on. So, without further ado, good. So can everyone see that? Is that okay?
Yeah, Peter, that's perfectly all right. Yeah.
Okay, that's great. Okay, so I'm going to talk to you about the
we muted all the mics so that there shouldn't be any disturbance.
Yes,
okay,
please.
Okay, so I'm going to talk to you about work done by me and my colleagues over several years, especially some of my former students here in Louisiana, Yu-Ting Lee, who now works at the University of North Texas, Tara Janelle from the University of Queensland, and my former colleague here, Alex Webb, who works in Hong Kong these days, as well as Danny Stockley in Austin and Jurek Bluestein at the Woods Hole Oceanographic Institute. So, I'm going to talk a little bit about monsoons and erosion. So what I wanted to point out to you was, well, sort of what is the monsoon? So the monsoon is a rather strange climatic phenomena that involves essentially reversal of the planetary scale atmospheric circulation that we normally see. So in the normal situation, where you have maximum heating at the equator and then hot air is rising, and as it does so, it precipitates. And in doing that, that's why we often get rainforests in tropical regions. And then usually then the dry air will subside in the mid-latitudes, which is again why we get things like the Sahara Desert or the deserts of southern Africa, for example. But of course, in Asia, we see almost the opposite of that. In the mid-latitudes in Asia, we have places like the Indo-Gangetic floodplains and the areas of southern China and Indochina where we would expect deserts. But of course, these areas are not deserts at all. Of course, one of the reasons that particularly attracts me to thinking about the Western Himalaya is the fact that we're on the edge of the rainfall. So you can see we have, of course, very high amounts of rainfall along the Western Ghats of India, along the Himalayan front itself, but particularly over Bangladesh and along the Arakan coast of Myanmar, and then, of course, further south here in the Andaman Sea. But where I'm interested in, the Indus catchment is on the edge of that. So this makes this area very sensitive to changes in the monsoon, and therefore an interesting place to look at to see how the variations in the monsoon have affected erosion and sediment transport. So I'm sure many of you have seen these types of models before, this idea about how the tectonics of Asia have resulted in a particularly strong monsoon. So I guess the general idea proposed by people like Peter Molnar was that the strong summer sun, it beats down on the top of the plateau, and that makes the air hot. And then this rises up, and in doing so, creates a low pressure system. And then that in turn draws in wet, moist air from the Indian or the Pacific Oceans, which then may rain out against the front of the mountains. So there's this relationship there between the tectonically generated topography and the climate system. And then actually more recently, about 10 years ago now, a couple of researchers, these fellows, Booz and Kong, that they were suggesting was that rather than the Tibetan plateau as being critical, that the thing that really affects the southern Asian monsoon is in fact the height of the Himalayas, right? So as the Himalayan barrier here is keeping the hot air over the floodplains, in front of the Himalayas, and that this is where the hot air and the low pressure system is generated. So there is a little bit of a debate about whether the Tibet or the Himalayas is more important. But in general, I think a lot more people now favor this Himalayan model, at least in South Asia. It's different in China, though. So there have been other influences on the intensity of the monsoon. One was the presence and then retreat of shallow seas in Central Asia, the so-called paratethys. So again, about 30 million years ago, we had this broad area of shallow seas stretching all the way from the Caspian up into the Tarim Basin. And this then contracts through time. It goes back to the modern Caspian Sea. So this is taken on a field trip I made in Western China 6-7 years ago. And that bed there is essentially the last marine bed in Western China. And it would be in this type of area here in the western bits of the Tarim Basin. So people believe that as that sea retreated, that it allows the continent of Asia to heat up more in the summertime and therefore intensify the monsoon. So we know that this has had an impact on the climate, and so people, of course, spent quite a lot of time worrying about how the monsoon has varied through time. And some time ago now, more than 30 years ago now, Jay Quaid and his friends were looking at this area up here in northern Pakistan. I think it was Potwar Plateau. And they were looking at these types of things. These are calcretes and soil concretions, and they looked at oxygen isotopes and carbon isotopes. And what they showed was that there was a big shift in these that started about 8 million years ago. Essentially, the story that they told was that there was a change in the vegetation that we saw in this region, and that essentially there was a transition from more so-called C3, which is more like trees, to a more grassy type vegetation that starts around 8 million years ago. And that this was, at that point, it was interpreted to reflect the onset of the Asian monsoon. And that didn't seem like such a crazy idea, because offshore Oman, in some of those boreholes I just showed you, they took some cores here and were able to reconstruct the history of upwelling. And particularly this little guy, this is a foram called Globigerina boloides. And boloides, this is this white pattern you can see in the satellite image here. This is millions and millions of these seen from space today. And this blooming of the boloides happens during the summer monsoon. So shortly after the cores were taken, the Dutch paleoceanographer Dick Kroon published this now quite famous chart where he showed that starting around 8 or 9 million years ago, there was a significant increase in boloides. And he suggested that this represented the onset of the South Asian monsoon, the wind systems that generate that upwelling. And that didn't seem to be such a crazy idea, because we also saw similar reconstructions of upwelling that were related, in this case, to radiolarian in the South China Sea, and also to wind-blown dust in the North Pacific. So it looked like something exciting was happening at that time. And people thought that that was the onset of the monsoon. So more recently, though, people have been looking at, they've been drilling, in fact, in the Maldives here. This very spectacular seismic image here where you can see, this is under the carbonate platforms of the Maldives. And they have this, you can see this massive carbonate platform edge, and then a huge, just dramatic drift deposit, which they color in yellow in the interpretation below here. And so this hugely asymmetric sedimentary mass was interpreted to reflect the onset of strong regional winds across the Maldives, starting particularly intensely after around, well, 12.9 or about 13 million. So they pushed the activity back some. So early strengthening, a little bit earlier than that, about 25 million, but a significant intensification starting, well, around 13 million years ago. So how does that development, our understanding of the monsoon, how does that relate to the tectonic evolution of the Himalayas and Tibet? And so we would expect, based on those cartoons I showed you at the beginning, that there should be some type of relationship, link between the development of the mountains and the monsoon. So if we're looking for something to be happening at 13 or maybe 8 million years ago, what were the mountains doing at that time? And in particular, I want to talk to you a little bit about the channel flow model for the Himalaya. This is this idea that the deep buried rocks that are exposed in the greater Himalaya have been brought to the surface through essentially by being extruded in a channel that is in shallow levels bounded by the South Tibet detachment and the thrust. And I guess the idea is it is the focused erosion on the southern edge of the Himalaya caused by the monsoon, which is removing material from the front of the range and allowing that deep buried rock to the flow to the surface. This would be an example. This is near Manali in northwest India. This is essentially the greater Himalayas in that area. So the idea is that strong summer monsoons cause focus erosion and allows deep buried rocks to come to the surface. So some years ago now, I tried to test this in a very simple type of way by looking at climate and erosion and tectonics all at once. So I used a weathering record from the South China Sea because it was the longest high resolution record we had. At that time, the longest records for the Arabian Sea went back to about 12 million years ago. But as you may know, the main central thrust begins to move around 23, 24 million and probably stops around 17. So we needed a longer record. And the South China Sea gave me that record. So what we seemed to see was that this is a proxy indicating dry or wet conditions, and so was that there was essentially drier back at the beginning of the Miocene, then getting stronger. There's a blip here, but then maximum intensity in the Middle Miocene, and then a weakening. So what was interesting, so that was South China Sea, and then if we come all the way across to the Arabian Sea, this was mostly from Indus Marine A1 offshore of Karachi. And this is a chemical weathering index here, again linked to humidity and climate. And again, we saw that blip there around the Mid Miocene, but then again, strong weathering in the Middle Miocene getting weaker through time. And this again supported the idea that this was the wet period and that it becomes progressively drier, essentially the opposite of what Jay Quaid and friends were showing. And indeed, in the Bay of Bengal, we see a similar type of evolution where we have a strong monsoon followed by a weakening here in the late Miocene. So in this telling, the change that we see in the carbon isotopes in Pakistan was driven not by a strengthening of the monsoon, but by a weakening. And interestingly, when we looked at the seismic stratigraphy of the Arabian Sea, seismic data in the offshore, we were able to make a sediment budget for that. And what we saw was that there was an increase in erosion rates of sediment being delivered to the Arabian Sea that was lower in the early Miocene, again reached a maximum in the Mid Miocene, and then began to decrease again. So it looked like the times with the strongest monsoon were the times also with the fastest erosion. And that on a very simple scale, you can see that there is this linkage here between climate and erosion. So if the model linking the mountains to the monsoon were correct, we would expect, therefore, that the greater Himalayas would begin to be exhuming fastest when the monsoon was strongest. And when we looked at argon-argon data from the Shivaliks in Nepal and in India, Northwest, and somewhat in Pakistan as well, we saw, well, an increase in erosion rate coming up here in the early Miocene with peaks. I'm not sure if it's important that they appear to be separate, but essentially the highest exhumation rates being in the Mid Miocene and then a decrease afterwards. And this was consistent with the idea that the monsoon was forcing the erosion of the mountain and generating the greater Himalaya, that essentially the greater Himalaya are formed partly because of the gravitational potential of the Tibetan plateau, but mostly they're formed because that's when the strong monsoon rains were falling. Of course, this does beg the question, if the monsoon really is getting stronger during the early Miocene, and then particularly in the Middle Miocene, is why is it happening then? I mean, the India-Asia collision occurs, 50, 60 million years ago. Why is it only get strong recently? Well, maybe the mountains only became taller recently, or maybe the Tibetan plateau only became large enough recently. I worked a few years ago on a model with my friend Alex Webb here, who proposed another solution to this. And our idea was that as India is thrusting below the Tibetan plateau, that the downgoing slab begins to tear off in both from the western and the eastern syntaxes and tear towards the middle before falling off entirely. And our idea was that as the subducting slab breaks off, that there's a flexural rebound. This big weight is lost and the Indian plate is able to rebound. And in doing so, it pushes up the high ranges of the Himalayas. We estimated by about 1 kilometer. And so in doing so, that would make that barrier that's keeping the hot air south of the Himalayas over the floodplains of the Himalayan foreland and intensify the monsoon. So the question is, of course, when is it doing that? We had a couple of suggestions about when that might be happening. Looking at magmatism in Tibet, we see, which is related to the tearing, and you could see that it was in the west, in the western syntaxis. Close to the western syntaxis, it starts in the sort of around 20 million and then gets younger down to about 12 million in the central part of the Himalaya around Lhasa. And we saw other features such as the timing of motion on the South Tibetan detachment, which again youngs away from the syntaxes and towards the center of the mountain belt. And then there are some other proxies here that also show progressive temperature increases towards the center of the range, getting younger and younger through time. So I looked actually in the foreland basin to try and support this. And I looked at detrital data along the entire frontal part of the Himalaya here, looking at zircon fission track and site. And so what we found was that, so these curves here are to show you where the dominant ages at different longitudes are. So So you can see like the western syntaxis is here shown in with the red curves, whereas the central part is in this light gray-green, sort of greeny bluey color. The eastern syntax is in the dark blue. And what you can see is in the fission track, all the old ages in the foreland are essentially all in Pakistan and northwest India, and that as we go to younger and younger ages, it's basically these the youngest ages are all found in the central part of the Himalaya around Lhasa. Likewise, in Argon, you can see the red curves associated with the northwest Himalaya tend to be older, and the youngest ages here are all related to this area around 83, 85, which is the central part of the range. So that was consistent with the idea of the mountains essentially uplifting in a progressive wave. So the high Himalayas would be uplifted early in the western and eastern syntaxes, and then get younger and younger towards the center, the progressive breaking off. And so we think that's what's triggering the monsoon to get stronger. So now what I want to do is talk to you a little bit about how sediment is then transported from these proximal regions, from the Himalaya and into the Arabian Sea. And then I'm going to show you a long-term reconstruction that we've been able to make based on those cores. So, of course, when we are thinking about how sediment gets from the mountains down to the bottom of the Arabian Sea, we're thinking, well, first of all, this is actually the Himalayas in Dharamsala. And so we want to take these large boulders and sandy deposits here. And of course, eventually they're going to have to make it to the Arabian Sea. This is a map of the Indus Submarine Canyon offshore Pakistan. And of course, that's the way that the sediment now gets into the deep Arabian Sea. So let's have a look at see how that works. So it's not a simple process, and this makes it problematic to reconstruct past erosion patterns using the deep sea sediments. And the reason that things are more complicated is because the rivers themselves the valleys store significant amounts of sediment in them for periods of time before they are released and able to flow to the ocean. So, for example, done here in the Sutlej Valley, showed in these colors here, you can see these different terraces that were mapped out by a group from Germany, Bodo Buchhagen and his colleagues from Potsdam. And what they showed that these terraces tended to accumulate at times when the monsoon was strong. And then this is a climate record here at the top. And so what we saw is that the valley fills up with sediment when the monsoon is strong, and then it gets cut and you form terraces when the monsoon gets weak. And indeed, further north of the rain shadow, this is in Zanskar, just north of the rain shadow. And my former student, Tara Janelle, was able to look at terraces in this region, on the edge of the Tibetan Plateau, essentially. And she saw a very similar sort of pattern where the valleys were filling up with sediment in the early parts of the Holocene and the end of the deglaciation when the monsoon is strong, and then they were being cut later. You see we have ages of 11, 12,000 up here, 8, 9, 8. This is all times when we know that the monsoon is strong. So the valleys fill up with sediment then, and then later they are cut as the monsoon gets weak. And indeed, further downstream, we see similar things happening in the floodplains as well. So this colorful image of the floodplains in Pakistan, India, Nepal. What you can see in orange shapes, sized valleys into the floodplains after about 10,000 years ago. So we know that there's a lot of sediment is coming out of the Himalaya and accumulating on the floodplains up until about 10,000 years ago, but that as the climate continues to dry, that these valleys are being cut and the sediment is being recycled down into the Arabian Sea. So you'll notice this isn't influencing Sindh and the central parts of Pakistan. It's only in the north. And you'll notice actually it does affect the western parts of the Ganges Basin. The Yamuna, for example, is affected, but the further east you go, you don't see it. And that's probably because this is influenced by the monsoon getting weaker. And essentially in the eastern Himalaya, it never gets weak enough to do that. So what happens to that sediment once it reaches the Arabian Sea? Well, we were able to look at that with a series of cores that we took along the Indus Submarine Canyon, starting from close to the coast, near where the river mouth is, all the way into the top, onto the top of the Upper Fan. This was a core taken some years ago by a Dutch group. And so what they showed, what that particular core showed, was rapid accumulation up until about 10,000 years ago, and then it's been abandoned. And that's, of course, what one might expect to be the result of sea level rise. What was interesting, though, is that the submarine canyon itself doesn't experience that. The submarine canyon continues to accumulate sediment in these cores in the central part of the submarine canyon, are active all the way through the Holocene when the sea level is high, in the way that one wouldn't necessarily expect. So where does the sediment come from? That might sound like a silly question, but we don't really, it's not totally clear that the sediment is closely linked to the Indus River. So we had to test that. And we did that looking at strontium and neodymium isotopes. So what is interesting to note is that the Indus River at the beginning of the Holocene has a substantially different composition than it does today, particularly in terms of strontium isotopes. So we had low values in the deglacial period, and today high values. And what we saw was all the sediment in the Indus Canyon have these high values. In fact, they're extremely close, within error of the modern river value. And that suggested to us that fine-grained sediment is being continuously delivered from the Indus River mouth into the deep water. It may not be getting into the submarine fan, but it's making it into the deep water throughout the Holocene. Interestingly, the sediment that sits on the shelf west of the canyon shows a contamination of sediment from Baluchistan, from the Bela ophiolite in particular. So, but once you get to the canyon and to the eastern cliniforms, we see this continuous sediment delivery from the river mouth. So we were able to look also a little bit at sandy material, because this is mostly muddy material. And it turns out that the sand and the mud are behaving. So we were able to get a handle on that by looking at zircon, uranium-lead dating of zircon. So this colorful plot of pie diagrams it's a little bit confusing, but essentially on the left-hand side, this is left to right is like offshore. So this is the river mouth here, and this would be the lower part of the canyon on the right. And then this is the y-axis is time. So the modern river looks like this. So the colors represent different populations of zircons that are associated with different sources. The blue in particular represents Himalayan sources. The yellow would be Karakoram sources, and the green Khoristan. And then the pink we thought were very young. They're probably related to Nanga Parbat, although they might be out of the eastern Karakoram as well. We couldn't really tell. So what you see here actually is that the pie charts that are near the river mouth actually have a substantially different pattern than the ones in the canyon. So like there's lots of Karakoram material here, but not in the canyon. So what we see is that there's a separation there. The sand being delivered to the river does not go straight into the submarine canyon. It's being recycled. And we also see actually some quite significant temporal variations. So the sand that's reaching the ocean changes its composition on quite short time periods. So you can see there's a big pulse of pink material here, which goes on for about 300 years, but then disappears again. So the modern river doesn't have much Nanga Parbat in it. So what we thought was happening this is the Submarine Canyon. So what we think is that, at least in the Holocene, that the Indus River is delivering sediment to the river mouth. The sand is being trapped near the river mouth, but the mud and silt is being advected in plumes and dumped into the canyon. So that is continuing to supply, but just not very quickly. So recently, my colleague Tara Janelle and I have tried to make a little sediment budget for the Indus during the Holocene, and this is what we came up with. It's presently in review, so you'll have to be patient if you want to read it, because hopefully it'll be done soon. So what you see actually is the lower reaches during the Holocene, the lower reaches of the river in Sindh. There's most of the sediment, 75% of it is coming out of the bedrock sources in the Himalayas and maybe out of glacial moraines, with very little is being eroded out of these mountain valleys. So although they look impressive, they're actually not storing a lot of sediment. The places that are storing significant amounts of sediment are the lower floodplain, the floodplains in the north, where I showed in the Punjab, where we saw those incised valleys. That accounts for about 11% of the total flux. And there's a somewhat undetermined amount, maybe up to 6%, is being fluxed in and out of the Thar Desert. So at the moment, that sediment that reaches the river mouth essentially has been ending up being stored in the Sindh alluvial plain, in the delta, and in these cliniforms on the shelf, the smaller western cliniform, the big eastern cliniform, and maybe even into the run of Kutch. So essentially almost nothing is getting into the canyon, very, very little, and nothing onto the submarine fan. So this is completely different to the glacial setting. So if you look at this in the glacial times, we see something completely different. So most of the sediment is going into the submarine fan at that time. But what's interesting to note is that of the sediment that's reaching the submarine fan, a lot of it is coming out of both of the erosion of these cliniforms and, of course, of the Sindh alluvial plain and the delta. As the sea level falls and the valleys are incised, all this interglacial era sediment is being reworked into the deep water. And so that means that the sediment that's accumulating on the submarine fan, it mostly accumulates when the sea level is low, when the glaciation is strong. But actually, most of the sediment that's deposited then was actually eroded during the last interglacial phase, maybe as much as 100,000 years earlier. So there's a disconnect there between the erosion in the mountains and the final sedimentation. So if you try and look at fine timescales, you can't correlate turbid ice in the Indus fan with short-term climate events on shore, because they're probably 100,000 years later than the original event. So with that in mind, I want to show you some of the records that we have from the Lakshmi Basin here. So we cored in 2 locations in Lakshmi Basin. These 2 sites, 1457 and 1456. This is the little seismic profile. This is the Lakshmi Ridge, and we cored here on the central part of the basin, and then 1457 is drilled closer to Lakshmi Ridge in an attempt to try and get some of the basement, which they were interested in, as well as the sediments. So let's look a little bit more about the submarine fan. We know, of course, the thickest part of the fan is up here under the Pakistani part of the shelf. Lakshmi Basin is a relatively thinner part of the unit of the fan, and of course it extends a long way offshore. And we also know that the upper part of the section has these dramatic channel B complexes, like these that I showed actually in my introductory slide, and that those also start in the Miocene as the sedimentation rate increases. But there is actually a significant Paleogene sequence there too, which is burying these earlier carbonate units. So the sections that we drilled in Laxmi are essentially equivalent to much of the Shiwalics, right? So they go back to about 12 million years ago. We don't have a longer record than that because it turns out that there was a very huge mass wasting deposit which actually damaged and destroyed a lot of the older record. So this is probably not a good place to drill, really. If you want long records, we're too close to the Indian margin, which is prone to collapse. Better to be drilling like on the Murray Ridge, probably. But you can see that these records that we had some big unconformities in there, but they do also cover this time of climate change that had been seen earlier in Oman. And we can see what the impact of this change was by looking at the chemical weathering record. And I guess the idea is that when you have a dry versus a wet climate, you get different minerals and different chemistries are associated with the soils, and that these are transferred into the sea when those soils are eroded. So I'm sorry, there's a rather complicated plot here. What I've got here are clay minerals on the right, and then a series of proxies here, potassium, aluminium, and the so-called chemical index of alteration on the right here, on the left here. And what we see is that particularly in the late Miocene, we basically a decrease in the amount of chemical weathering, both in terms of the CIA, the potassium, aluminum, and then ratios such as the illite crystallinity or the kaolinite illite chlorite. Kaolinite is a chemical weathering product, whereas illite and chlorite are physically weathered. So when that decreases, it means that the amount of chemical weathering was decreasing. So as the global climate was getting colder and the Indus Basin was getting drier, the amount of chemical weathering was deep. And this is our curve for the carbon isotopes in the foreland basin. Again, you see that 8 million year transition quade found in the Potwar Plateau is occurring essentially just after when these drying trends. So we do see an impact, you see there, of changing monsoons and the intensity of chemical weathering. But does it have an effect on the patterns of weathering as well, the patterns of erosion? And so this is one of the great reasons to work in the Indus Basin, is that we know that the source regions have wildly different isotopic compositions. In terms of neodymium, for example, we have very negative values in the Lesser Himalaya, especially the Inner Lesser Himalaya. And then, of course, very positive values in the Trans-Himalaya and in Khoestan, with intermediate values in the Karakoram, and then in the Greater Himalayas and Outer Lesser Himalayas. So what we did was we looked at our record here from the Arabian Sea. So the blue dots here are the new data we got from the ODP boreholes, and these brown dots here come from the Indus Marine A1 well on the Pakistani shelf. And what we've got here is like a long-term running average. So what we thought was that some of the samples had values that were so high in epsilon neodymium that they were probably being contaminated by flux of material from the Deccan Plateau. So we didn't include these, but we just concentrated on the ones that really looked like they were from the Indus River. And so what you see, the simplified version is here in the gray. So, and what we were seeing was essentially an increase in epsilon neodymium values going from about 16 million up until about 8, and then basically a decrease, especially after about 4 million years. So what's causing that Well, if we look in this cross plot here, you can see, here's neodymium against strontium, and we have the Trans-Himalaya overlap with the Deccan, so we can't easily tell the difference between those two. But of course, the Himalayas have basically very negative epsilon neodymium and very high strontium values. And so what we think is happening is that from 16 until about 10, there's the proportion of material coming from the Karakoram would be increasing. But that after 8 million, we see an increase in Himalayan erosion, especially after 4 million. And of course, that's a time when the climate's drying. So we could get at this a little bit further by looking at zircon dates. So again, zircon is characteristic of different parts of the Himalaya. We know that the Greater and Tethyan Himalaya have this big peak at about 1,000 million years, where the Inner Lesser Himalaya have this older peak here at about 1,800. And of course, the Karakoram and Kohistan, and particularly Nanga Parbat, have these extremely young values. So this allows us to know where the sand has been coming from. So this is some of the data that we've had published. Essentially, these sediments at the top are from the Lakshmi Basin, and these are the various source regions. Again, Kohistan, the Lesser Himalayas, the Karakoram, and so on. And I put some colored strips here to show you where the sediment, what these peaks mean. So you can see like this yellow strip here is characteristic of the Lesser Himalayas. So what's interesting is that we can see this actually in the modern river, actually near the river mouth at Tata, near Karachi. And when we look at the old submarine fan deposits, you notice that we don't see this at all until we get up to this value. So this guy is only about 1.9 million years old. So we actually don't see any significant Lesser Himalayan erosion in the Indus fan until very, very recently, until 1.9 million. You'll notice that all of the Indus submarine fan sediments I'm showing you here have these blue values, and those are typical of Kohistan and the Karakoram. So these sands are not coming from Peninsular India. They're coming from the Indus River. But we don't see the Lesser Himalayas until quite recently. And in fairness, we even have to say that the highest peaks related to the Himalayas, the Trans-Himalaya, sorry, the Tethyan Himalaya or the Greater Himalayas are also relatively young. We can see this in a statistical diagram here, a so-called multi-dimensional scalar plot. And here I plotted the different sources here in red and the sediments in blue-green colors. And what you can see is a transition here, the oldest grains here plotting on the right, closest to the Karakoram, at 15 or 8, 7 million. And that as we get younger and younger, those sediments are becoming more and more Himalayan in character. So the modern river that I show in blue here is actually much more Himalayan than it used to be, say, 8 million years ago when the Karakoram was dominating. So as the climate and the tectonics have evolved, so has the provenance of the sediments. And it was interesting to me to correlate this with a reconstruction done by my colleague Alex Webb, who in fact shows in his cross sections here that in this case, the pink is the Greater Himalayas, and this purple brown material here are the Inner Lesser Himalaya. So what he's showing is that both of these units actually only come to the surface after 5 million and around 1.9, which is actually consistent with what we're seeing here, where the Lesser Himalayan peaks come to the surface quite recently. This is a little bit different from what we've learned from the Shivaliks in places like Jwalamukhi in northwest India that suggest much earlier unroofing of the Lesser Himalayas. But that suggests that that's just a local effect, because the submarine fan is looking at the whole basin. So the Lesser Himalayas, and maybe relatively recent in the north. I want to spend just a minute or two thinking about Nanga Parbat, because a lot of people worry about Nanga Parbat being a big source of sediment. and especially as the eastern Himalayan syntaxis is believed to be a big source of sediment. So recently we acquired some samples from two valleys close to Nanga Parbat at Tato and Gorikot here, and we again looked at zircon in them. So actually, unlike the older zircon ages that were generated by Peter Zeidler, it's interesting, although we have the young peaks here at both those areas, we also see this older 1.8 billion year peak, which is associated with the Lesser Himalayas. And what was interesting to note is that although the various rivers upstream are there, places like the Hunza and Gilgit rivers here, they all have the young peaks there, but of course not that old one. So it's interesting that upstream of Nanga Parbat, the rivers have only young peaks. Then downstream of Nanga Parbat, around the Attock Bridge, south of the Tarbela Dam, again, we see lots of the young material, but really not very much of that old. So it looks like the sediment pouring off Nanga Parbat is not greatly affecting the bulk composition of the Indus River. It's a very impressive mountain, but it's not producing a lot of sediment. Yeah, you can see this again. This is another one of these multi-dimensional scalar diagrams where the river at Attock here, it has some similarities to the sediment at Tato, but it's actually closer in composition to the Hunza and Gilgit rivers and the eastern Karakoram. You can see this breakdown actually of the river, the Indus River at Attock Bridge here. This is in zircon, but we have to also calculate a dilution effect related to the relative productivity of these source regions. So you can see actually here that maybe, you know, a quarter of the zircons in the Indus River are coming from Nanga Parbat, mostly from the Tato type sources, not Gorikot. But once we account for the fertility of the river, you can see that becomes quite small, just a few percent, and that most of the sediment is coming both either from the western Karakoram, the Hunza Gilgit area, or the eastern Karakoram, the eastern Karakoram in northern India and eastern Pakistan. So we can put all this together and look at the long-term development of the area and see how that compares with the climate. So what we see is, that, as I mentioned before, a progressive increase in Karakoram influence. And we see this in the zircon here, especially this green and orange looking stuff here at Karakoram. And that after a peak in the late Miocene, as the climate gets drier, we see actually decreasing erosion from these sources and increasing erosion in the Himalaya. And actually, that's quite surprising because, of course, the Himalaya is the place where the monsoon is strongest. So you might expect that as the climate gets drier, you would have less erosion from the Himalaya, not more erosion from the Himalaya. But that doesn't appear to be what's happening. The variations in the monsoon appear to be affecting the rate of erosion, but not the location of erosion. And in fact, we can use these zircon numbers and unmix the sources. And in doing that, we come up with a little plot like this. So again, the Karakoram here is shown in green, and Kohistan and the Trans-Himalaya in purple here. The Himalayas, the Tethyan and Greater Himalaya in blue, and the Lesser Himalaya in this burgundy color. So what we see is a progressive decrease in flux from the Karakoram and an increase in flux from the Himalayas, although the climate is drying. So we were actually, after thinking that the monsoon is dominating the erosion during the formation of the Greater Himalayas and driving the channel flow, if you like, that subsequently the erosion patterns here are being driven by solid rock uplift, that the tectonic forcing up particularly the Lesser Himalayan ranges and that they are then allowing precipitation to occur against them, especially when the monsoon is strong. So we believe that the location of erosion in the mountains is being guided by solid earth forces, but that the rate of erosion is being driven by the monsoon. So I'd just like to wrap up at this point. So what I hope I showed you is that we saw monsoon intensification, initial intensification starting at the early Miocene, probably being driven by that breaking off of the Indian lithospheric slab, the tearing and the rising of the Himalayan barrier. And so actually the long-term weathering trends indicate less chemical weathering as the climate dried, which is actually the opposite of what was predicted by Raymo and Ruddiman in their hypothesis about the links between uplift of the Himalayas and global climate. So the strong rains increased erosion and drove the exhumation of the Greater Himalayas. But since that time, we've used neodymium and isotopes and strontium to show more erosion of the Himalayas starting around 6, and especially after 2 or 3 million, especially in the Lesser Himalayas. And that we can also say that Nanga Parbat is an impressive mountain, but it's not a big producer of sediment and does not dominate the sediment record. And that actually rather late unroofing of the Inner Lesser Himalaya and maybe even the Greater Himalayas is consistent with the structural models. And so it's hard to see how the patterns of erosion are linked to monsoon intensity. So that's probably the patterns are more related to tectonically driven rock uplift. So before I finish, I just wanted to make 1 or 2 little quick announcements. First of all, if you're interested in the Asian monsoon, you can attend a weekly series of monsoon lectures. They're on Wednesdays, actually. And they're called the Monsoon Seminar Series. And we have a website, the Monsoon Geo Seminars website, and you can see what's coming up, and you can also see all the previous lectures, just like this one, which are available on YouTube. And if you want to be included on a weekly mailing list that will send you the link to next week's talk, you should send me a little email and I'll add you to that list. So that will keep you up to date. And then actually, if you're also interested in how people and the monsoons have interacted, I recently had a book published about the development of civilizations in Asia and its link to monsoon rains and the rivers of Asia, which has just recently been published by Cambridge University Press. Don't write and ask me for a PDF because I don't have one. So I'm sorry, but I just don't. So
we will find somewhere.
Cambridge don't want me to have one, otherwise I might give it away to people and then nobody will buy the book. So that's
they're already clever, Peter.
Anyway, I will stop at this point, and if you have any questions, I'll be happy to answer them. But thank you.
Thank you very much. That was a very nice presentation. Yeah.
You can end the presentation now.
Sure.
Yeah. So if there's anyone interested in asking Peter about the talk, then you can raise your hands.
Yes, Professor Bob wants to say something, but his mic is off. Professor Bob, please unmute yourself. You are mute. Your mic is still mute.
It is, isn't it? Can we turn it off for him? No.
No, we can't. He muted himself.
Yeah.
Only he can unmute himself.
Does somebody else want to ask a question while we're waiting for him?
You can raise your hands. So I think that's that's someone's talking between, hasn't muted the.
Yes.
We have Andrew. Andrew, please go on with your question from Peter.
Hi, Peter. Thank you so much for a wide-ranging and very stimulating talk.
Thank you, Andrew.
The one thing that I'm I guess confused about now at the end is how you can say anything about erosion rate from sediment volume, given that you have showed that on many spatial and temporal scales that sediment storage is occurring and modulating at least provenance through the depositional and distributary system. So given that some sediment at any given time is primary bedrock erosion and some is stored from some other time scale, how do you actually deconvolve those two?
Well, yeah, well, that's a good question. And the only reason that we can do that is because the budget I show you is really quite low resolution. So we're just looking at the entire Pleistocene. So if you were trying to break that up onto shorter timescales, you would struggle to do that. It's just that the average sedimentation rate in these big over long time periods, you can't store sediment in the Thar Desert for 5 million years. So you're right, on shorter time scales, this buffering effect is quite serious. And maybe even there are some repositories of sediment where the sediment could be stored a long time.
Isn't the
foreland, of course.
Isn't the Himalayan foreland a massive sediment repository?
It is, and we do know, of course, it is. Well, there's two ways of recycling sediment out of the foreland basin. One is to scrape it off into the Shiwaliks and uplift it and erode it. And so there have been attempts to try and see how much of this recycling takes, how much of the total flux is related to erosion out of the Shiwaliks. It looks like, based on terracing ages in places, mostly in Nepal, I think work done by Avawak and friends, it looks like something like 10, not more than 15% of the total flux now is coming out of the Shiwaliks. The other way of doing it is, of course, is to invert the foreland basin. And we know that happens in a few times. We know that there is an inversion event around 16 million, which is probably related to the Mid Miocene climatic optimum. And there's another big one. Of course, the big one is the one before around 20 million, which is why we don't have any Oligocene in the foreland basin, because it's all bypassing the foreland basin at that time. So let me think. That's in the Oligocene and early Miocene. I did once work out how even then, the problem is that's also a time of very rapid erosion in the mountains. So I think even at that point, the recycled signal does not dominate over the new erosion. So, but I think provided you're willing to average things over a relatively long, like a million-year timescale, it's not a bad record. The main problem is you can't do it on short time scales because of this buffering and recycling effect. Right.
We have Dr. Syed Harun Ali from Sargodha University, Pakistan. Doctor, you can ask your question.
Hi, Professor Peter. Thank you for the presentation. In one of your illustration, you show in Indus offshore a carbonate platform.
Yeah.
So, do you think that there is any link of generation of secondary porosity in those carbonates with the meteoric diagenesis or mixing zone diagenesis or the influx of fluvial systems that disturb the overall and later on burial of the carbonates? So in your opinion, you have seen the seismics, you have seen the cores. Can you please put some light on that?
Well, actually, I haven't seen the cores. Those are all industrial cores, so I've actually never seen those sediments. But I don't think they were ever really exposed to the air. That they were always marine, and then they get buried under the fan. I mean, essentially, there's a rather dramatic collapse of the margin for reasons that I'm not always entirely sure of. Actually, I know that we thought that it was related to the Deccan plume, but it can't be, actually. The timing is completely wrong. But it was my impression that they were very porous. They're like reef carbonates. The main problem is that they don't have any oil in them. I mean, that was drilled by Total, wasn't it? So they drilled them and they didn't find it. So I think that they're good reservoirs. They just don't have any charge.
We have Catherine. Catherine?
Let's see. Can you hear me?
Yes,
Yep.
I can hear you.
Thanks for a very interesting talk. Well, I have a rather general question, and I hope it's not too simple. And that is all the many details that you provided about the chemistry and the sediment accumulation rates and so forth on the Indus Fan. How much are they telling us about the height of the source areas versus the changes in the drainage patterns? And I realize those are interlinked variables, but I'm thinking about river patterns of river capture and the heights of different regions. And I'm asking that question as someone who's really interested in how mammals ever could have gotten into South Asia, given the height of the mountain barriers, to the particularly with respect to animals living on the western side of the western syntaxis.
Right. So I don't think we know anything about the height of the mountains from what I showed you. I mean, just because a certain area was eroding doesn't necessarily fast or slow. It doesn't really tell you anything about its altitude. River pans are a different matter. So about 15 years ago, I thought that this shift to more Himalayan values in the fan was reflecting, I thought it was reflecting the fact that the eastern tributaries, like the Jhelum and the Sutlej and the Ravi, and were all being captured into the Indus during the late Miocene. And I completely changed my mind about that. Partly because of some of the records I showed you about that. So when I thought about that, I was assuming that the rivers are all the same composition in the past as they are today. But of course they weren't, were they? So, before the Lesser Himalayas were exposed, I mean, now the Sutlej is full of Lesser Himalayan detritus, but it wasn't like that before the Lesser Himalayas were exposed. So, essentially, that was built on a false assumption. So I don't think, I think that probably the drainage has been more stable. I mean, than I thought at that point. I do think that some of the rivers may have been lost or gained. So we do know that the Yamuna used to flow into the Indus in the past, as recently as 50,000 years ago. And it probably did it before that as well. But so I feel like the Yamuna is like the weird river of South Asia. It can go both ways. And it's possible that in the past, some of the others, like the Sutlej, maybe the Sutlej used to flow into the Ganges, for example, and has been captured. But I don't think the really big scale erosion capture that I was worried about, I don't think that's justified actually anymore.
So just one last question, then I'll turn it over to others. Do you think then that the Indus River as a major drainage as it is today is very ancient?
Yes, I do.
I mean, ancient all the way back to the early Miocene.
Oh, I think it's Eocene.
Eocene, okay.
Yeah, I think, or at least I think the river has been in the suture zone in Ladakh and in and northern parts of Pakistan essentially since the collision. I suspect that river was supplying the Katawars sequences in western Pakistan. So, like, yeah, and because, well, you can add and maybe take away some of those Himalayan tributaries, the Punjabi tributaries, but the mainstream of the river, I think, is very old indeed. Yeah.
Thank you.
Professor Peter, I have a short query.
Sure.
I went to a conference paper and they were showing some pattern of monsoon rains in Pakistan, and their data shows that the monsoon pattern was shifting toward southwest in Pakistan, and now in last 20 years we have monsoon rains. They are reaching toward parts of Balochistan, which were not reaching to these areas in before 20 years ago. So, what could be possible reason, and how much they are changing?
Well, this is, yeah, because it's a complicated question, this, isn't it? So, in general, the warming of the planet is making the monsoon stronger, but also more stormy. So, you know, like some of the events we saw in, was it 2010? Was it 2010 or 2008 where there was the flood?
2010.
Right.
Yeah.
So that you might see more things like that. It depends. There are two opposing factors here. One is that as the Earth is getting hotter, the monsoon in general is getting more erratic. It's stronger, but it's more erratic. And the long-term thought is that actually places like the northwest floodplains, like Punjab, would be getting drier. On the other hand, although the monsoon may be getting stronger and stormier, pollution is also an important factor, because it turns out like pollution from industrial or urban centers has an effect of dampening the monsoon, because essentially because the monsoon is formed when the land is getting hot, and those like the pollution provides a cover and stops the land getting hot. So it works in the opposite direction. So what happens in the future depends a little bit not only on our CO2 emissions, but also in pollution in that area. It particularly, well, I suppose in Pakistan, particularly in Pakistan, but of course all across the floodplains along the entire Himalayan foreland basin. So, you know, I think the general thought is though that much of the northwest might be getting drier. But you might get these catastrophic storms, which is really not, probably not what farmers want to see, right? They like gentle rain.
No.
Yeah. I think that's pretty much it, Peter. We don't have any more questions. Thank you very much for your very interesting talk.
It was a pleasure.
I don't see Bob around. Randy?
His mic is still mute.
Yeah, Bob is here, and I don't know. Okay, yes. So I think we should rather conclude it now. Thank you very much, Peter. I think the next speaker for Wednesday seminar is Andrew.
Yes, it's Andrew.
I don't know if Andrew is here, but we'll like to see all of you on coming Wednesday. Take care and see you there. Thank you very much for everyone joining. Thank you. Bye.
Bye-bye.
Bye-bye.